Hello and welcome. This refrigeration cycle problem involves a flash chamber. You can read the problem, but let me quickly go to the schematic and the TS diagram. The schematic is a little bit fuzzy, but still you can see in the TS diagram I have just drawn. We'll call this the bottom cycle and the top side. I mean bottom part and top part, in the lack of better word. In the bottom part of the cycle, we have 1 to 2 is the isentropic compressor. And also on the top cycle, the compressor is 2 to, let's start from the top cycle, go from 9 to 4, isentropic compressor. 4 to 5 is the condenser, and 5 to 6 is the expansion valve. At 6, we have this flash chamber. Its job is to separate the saturated vapor at state 3 from saturated liquid at state 7. So this is what gives us the connection between how the mass flow is separated. And we have from 7 to 8, we have again expansion valve, and 8 to 1, we have this evaporator. The advantage of using the flash chamber is that notice the heat is absorbed from here to here. This area is kind of the cooling capacity you can show from the TS diagram analysis. If we didn't have flash chamber, we would have probably directly throttled from state 5 all the way down here. In that case, the cooling capacity would have been only this much. Can you see how the cooling capacity is increased because of using the flash chamber? So just a couple of more things. The mass flow rate, you will notice, is not supplied, but the 3 different pressures are supplied. So we'll call this pressure at the top, pressure at the bottom supplied, and pressure at the middle. Also, the mass flow rate we'll assume is 1 kg per second at the top. And then in that case, the mass flow rate here on the bottom cycle will be, as you can see, it is separated by quality. So this would be, the mass flux here will be, 1 kg times 1 minus x at 6. So with that in mind, this is 1 kg, I'm sorry, 1 times 1 minus x6 is the liquid part, and 1 times x6 will be the vapor part. So let's go. I have already solved the problem, set it up. Let me first show you what app I'm using. TESTapp, obviously. In that module, if you follow the open system branch, specific branch, and come to the vapor compression and gas refrigeration system. And in this case, we have a phase change fluid as the working fluid. So we click there, and clicking here brings the app, which I have already done here. So let me first go to the I/O panel and show you the variable I have set up there. The m dot top, I'm calling the mass flow rate of the top cycle, 1 kg per second. Then, as I just now said, m dot bottom will be m dot top times 1 minus x6. Of course, the difference will be the one that is the vapor. Again, the 3 pressures given are P top, P bottom, and PM are defined here. Once we click the calculate button, they're calculated here, and they're posted right here. So these values will be picked up, and we can use them in state panels. State panel, state 1, you recall, again, I'll suggest that have a schematic in front of you to follow what I'm doing right now. State 1 you'll find is the inlet state to the compressor, the bottom cycle. Pressure is known, and the mass flow rate, we just borrow the symbol from the I/O panel. And of course, at state 1, it's the end of the evaporator. The quality must be 1 for an ideal cycle. So state 1 is found. State 2 is the isentropic. As you can see, it's the isentropic exit state. So entropy is known, and the pressure is the pressure of the middle pressure, we call it. And of course, the mass flow rate is the same. State 3, which is kind of what is coming out of the flash chamber. So it's still at the middle pressure, and mass flow rate will be the top cycle minus the bottom. Top minus bottom would be the mass flow rate going at state 3 if you look at the diagram. And of course, the quality is 1 because that's what the flash chamber does. It separates vapor from liquid. So this is the saturated vapor part. State 4 in our diagram is exit of the compressor, top compressor. So actually S4 equals S9. 9 is the inlet. Unfortunately, the numbering has not been the best, but still you can. So when you solve for state 4, you will find it cannot be evaluated because we don't know S9 yet. So there will be a white background here. But once state 9 is found, or we click a super calculate after we enter all variables, this will be determined. And of course, m dot 4 equals m dot top cycle. State 5 is simple. It is the exit to the condenser. So therefore, pressure is still at the top pressure and quality will be 0 because saturated liquid. And the mass flow rate is, of course, m dot top. Now we have the expansion valve. So state 6 will have enthalpy same as enthalpy at state 5. And of course, the pressure is now reduced to the middle pressure. And of course, m dot t is known. It is still m dot t. State 6 is found. For state 7, it is the liquid, the saturated liquid coming out of the flash chamber. So this quality is 0, middle pressure, m dot bottom. State 8, again, it's expansion valve, so enthalpy remains constant. This is the bottom expansion valve, pressure bottom, mass flow rate is the bottom, so state 8 is found. And now for state 9, which is the exit state to the mixing chamber, the pressure must be the same as middle pressure. But to get the second condition, we use a heat transfer, energy balance on the mixing chamber. And I have done that, in the PowerPoint, which is right here. So we take the mixing chamber, take a control volume around it, make a system around it, and then we have state 3 and 2 are coming in, bringing in energy, enthalpy flow energy, and going out m dot 9 times H9. That gives us a formula for H9, which we substitute here as when I put the pointer, as you all know, that when we put the pointer over a variable, the formula, etc., shows up in this help panel. So I'll just show you when I put the pointer over H9, you can see that I have transcribed the formula right here. We could take a look at the TS diagram to make sure everything is fine. Of course, it's a complex diagram. You have to zoom in there to make sure to see that state 9 is actually in between state 3 and state 2. And it will be. They're just crowded, so you have to just zoom in and see that all the states are correctly displayed here. Let's go now to set up the devices, which are kind of straightforward now that we have calculated all the states. Device 1 is the compressor, the top cycle, going from 9 to 4. This is the isentropic compressor, and the compressor power is found. Similarly, we do device 2, the top condenser, the heat transfer is calculated. And then device 3 is the expansion valve, 5 to 6, and work transfer is 0, obviously. That produces heat transfer to be 0, which we already know. So this serves as a check that the energy balance is correct over the expansion valve. State 4, device 4 is the flash chamber. For that, we pick multi-mixing. Notice the 3 kind of device, and multi-mixing is chosen, and that gives us 2 inlets and 2 exits at the most. In this flash chamber, we have just 1 inlet, state 6, and 2 exits, 3 and 7, and the second inlet is left blocked. We enter the work transfer to be 0, and the heat transfer should be calculated very close to 0, as you can see it is. The device 5 is the bottom expansion valve. Again, heat transfer should be calculated as 0, as it is. And device 6 goes between 8 and 1, so it's the condenser, the evaporator, and you can see that the heat added on the evaporator, that's the cooling load for this particular problem. And finally, there'll be couple more device. So let's go look at device 7. Device 7 is the bottom compressor. The work transfer is calculated. And device 8 is the mixing chamber. We haven't done that, so it will be a mixing chamber, will be again multi-mixing, where the two fluids are allowed to mix. Notice that if we select in a heat exchanger, closed type heat exchanger, we'll select multi non-mixing. But in the mixing chamber, what we got here is state 3 and 2 mixing together, producing state 9. We'll leave the other one blank. And if there is work transfer 0, then heat transfer should be calculated to be 0, because that's the energy balance we used. Exactly 0. So now that all the devices have been calculated, the cycle panel should be just about ready. So we go there, and as we do a super calculate, that would be a good idea always, just to update everything. We find that all the COP etc. have been calculated. Here's the COP, here is the net power in, and that must be equal Q dot net, and W dot net must be equal. Let's check on it. So all the desired variables of the problem now have been found. Of course, we can do parametric study by going to the I/O panel and changing a parameter, isolating the parameters and changing it here. Suppose we say, what if the middle pressure is not 400 but a little bit higher? Let's say it's 600 kPa. So we do a calculate that updates these variables, and we go to the cycle panel to remember what we got. So let's say the COP is 3.49. Let's write them down, and the cooling capacity is really Q dot in this problem, which is 105 kilowatt. So now what will be the impact of our parametric study? Just do a super calculate. All the calculations are updated. Come back. Notice that the COP has increased, as you can see here, and the cooling capacity also is increased. So that's how you can optimize what will be the right. But if you keep increasing, we'll soon find the effect of flash chamber will not be so good, because if you make the flash chamber pressure too high, almost close to the top cycle pressure, then that means you don't have a flash chamber. Anyways, refrigeration is covered in chapter 10. You can find a whole lot of problems in the refrigeration section of the problem section, and in chapter 10 it discusses various other cycles, various other modifications to this cycle.